This lecture discusses the concavity of functions, and then this introduces how to use the second derivative test to detect any local extrema. So first, what is the definitions of concavity? So if you have a functions f of x is a differentiable functions on an open interval, then the graph of f is concave up on that interval when the derivative f prime is increasing on the interval, and the concave downward on I when the derivative of f is decreasing on the interval. So let's say this is the function f of x, and on an interval I, and the function's f of x is concave upward when it has this shape on this interval I, right? From A to B. This is upward concavity. And then this is the shape of the graph of f of x when f of x is concaved downward. On the interval from A to B. Okay. And then by the definitions, when the graph is concave up, that is when the derivative functions, right? The derivative f prime of x is increasing from left to right. This is 1. Like that, and you can see that the derivative, what is the derivative? The derivative is just the slope of the tangent lines. So you can see that the slope of the tangent line from left to right increases when the function is concave upward. And when the function is concave downward, then you can see that the slope of the tangent lines are decreasing from left to right. All right. So let's look at an example here. So this is the functions, a polynomial functions x cubed minus 2 of x. And then as you can see that if I move the point on the graph, this line, the purple line here, is the tangent line to the graph at the point. Okay, and you can see the tangent lines moving, and the slope of the tangent lines changing from positive to negative, and it's increasing and decreasing. So if we look at the table here, this table shows you some value of x, and the derivative, the corresponding derivative functions, right, at the same point, the same value, and the corresponding second derivative of the function at the same point. And if we look at these functions, we can find the first derivative of this function is 3x squared minus 2. Right? And then we can find the second derivative of this function is 6x. Okay. So then we can find the critical point of the functions. Critical point which is 3x squared minus 2 equals 0. So the critical point should be plus and minus 2 over 3, or the critical point. And then if you find the second derivative, and then you set the second derivative equals to 0, that is when you get an inflection point. So what is an inflection point? Inflection point is a point when you when the function is changing from concave downward to concave upward. Is a point where the function is changing, the concavity of the function changing from upward to downward or from downward to upward. So those are the point of inflections, right? And also point of inflections are the points where the second derivative does not define. So then we found that 0 is a point of inflections. We found that plus and minus square root of 2 over 3 are critical points. Then when we look at this table here, so when x equals to negative 2 over 3, like square root of negative 2 over 3, then f prime of x1 equals to 0, which makes sense, right? And then f double prime of x1 is negative. Okay. And then when we go to the second critical point, again, because it's a critical point, so the derivative is 0. And then the second derivative at this point is positive. Okay. And then you can see that on this graph right here, the function is concave down from negative 2 to 0. The function is concave down. Okay. And then if we look at the functions from 0 to, let's say 0 to 2, the function is concave up. Okay. So on the downward concavity, if you have a critical point, and then we found that this is the critical point, and we know that it's negative 2 over 3, then the critical point here is one of the local maximum. Okay. And then on the intervals in which the function is concave up, and if you have a critical point in this interval, and we know that this critical point here is 2 over 3, then this point right here is a local minimum. So what does that tell you? That tells you once you determine on which interval the function is concave up or concave down, and if there is a critical point that is in those intervals, then you can determine whether that critical point is a local maximum or a local minimum. So in this case, if the critical point is in an interval which the function is concave down, then that point is a local maximum. And in this case, if on the concave up interval, and if you have a critical point that is in the concave up interval of the function, then that critical point is a local minimum. So we look at the table right here, we can see that at x equals to negative square root of 2 over 3 right here is a critical point because the first derivative equals to 0. And then the second derivative at this point is negative. That means the function is concave down at this point, right? And the function is concave down, then you can conclude that this point here is a critical, is a local maximum. because the function is concave down, then the critical point is the local maximum. And then if you look at the second critical points, square root of 2 over 3, we know that is a critical point because the first derivative equals to 0. And then we look at the second derivative is positive. It's positive, that means this critical point here is on the concave up interval. Right? If it's on the concave up interval, then this critical point is a local minimum. And using the second derivative to determine whether a critical point is a local maximum or a local minimum, it is the second derivative test. Again, using the first derivative, you can determine critical points of your functions, and critical points can be either local maximum or local minimum, right? And then you can use a first derivative test to determine whether a critical point is a local minimum or a local maximum. But then using the second derivative, you can determine on which interval the function is concave up or concave down by finding all the point of inflections. Okay. And once you determine the concavity of your functions, then you can use a second derivative test to determine whether a critical point is a local maximum or a local minimum. Again, if a critical point is on a concave up interval, then that critical point is a local minimum. If a critical point is on a concave down interval, then that critical point is a local maximum of the functions. So the theorem 4.7 in the textbook is a test for concavity, and then we already discussed about it, right? If the second derivative of x is greater than 0, then the functions is concave upward. If the second derivative is less than 0, then the function is concave downward. And you can find the point of inflections. The point of inflection is a point where the function changing from upward to downward or from downward to upward. So the points of inflections in theorem 4.8, it says that if a point C is a point of inflections of the graph f, then either the second derivative of the function at that point equals to 0, or the second derivative at that point does not exist. All right. So how can you determine on which interval a function is concave up or concave down? You can use this table here. Is very similar to the table that you used in the previous lecture when you determine whether the function is increasing or decreasing. So first, in concavity, finding concavity, you need to find point of inflections. In order to find point of inflection, you need to find the second derivative of the functions f of x. Okay, so you need to find the second derivative and set the second derivative equals to 0 to find point of inflections. So once you have points of inflection, you can put it in this table here. So for an example, we found, let's say we found 2 points of inflections, and we have left endpoint and the right endpoint here. So from this left endpoint, right endpoint, and the 2 points of inflections, we can create the test interval. So test interval will be from the left endpoint to the, let's say, x1, and then x1 to x2, right? And then x2 to the right endpoint. So I say L and I say right endpoint. So we have, using 2 points of inflections, we have 3 intervals. And then in each intervals, you want to pick just a random point, right? A test point. And I would say, say it's x. We would use this point of inflections. So pi, right, 1, pi1, and pi2, and pi2, and then r. Okay. So in each interval, I pick a point, a test point. So x3, and then I evaluate these 3 test points using the second derivative. And then I just need to find the sign of the second derivative. If it's positive, and just assuming the second derivative is positive and then negative, and this is positive. That means the functions, if the second derivative at this test point is positive, that means the function is concave up on this interval. If the second derivative is negative, then that means on this interval, the function is concave down. And again, if the second derivative at this point here is positive, that means the function is concave up on this interval. Okay. So this is how you determine whether a function is concave up or concave down on a certain interval. And then you can use a second derivative test again. The second derivative test will help you determine whether a critical point is a relative maximum or a relative minimum. So if the second derivative functions at c is greater than 0, when c is a critical point, that means f has a relative minimum. Okay, because if second derivative of c greater than 0, that means c is in the interval on which the function is concave up. The function is concave up, then c here is a local mean. And then if the second derivative at c is less than 0, that means c here is on the interval, concave down interval. That means c is a local max. All right, and then again, you can put, you can create a table, you can populate a table to illustrate the second derivative test. For an example, if for some function you found 3 critical points, right? Points where the first derivative equals to 0, and then you just need to find the sign of the second derivative at this point. So let's say x1, x2, x3. Okay. And then you just plug these 3 critical points into the second derivative. And then you find the sign of those values. Let's say 0, greater than 0, less than 0, for example, right? Then if the second derivative at this critical point is greater than 0, that means this point, x1 is a local, is greater than 0, is a local min. Okay. Also, x2 is also a local mean. About x3, the second derivative of x3 is less than 0. That means x3 is a local maximum value. All right, let's look at an example. So example 9, part 1. Find other points of inflections and discuss the concavity of the graph, right, of the functions. Again, in order to find points of inflections, we need to find the first derivative. So the first derivative of this function is should be 3 over x squared times e to the negative 3 over x. And the second derivative of this functions is using product rule. You find the derivative of this function, which is 3 over x squared e to the negative 3x, and you multiply by 3 over x squared plus negative 6 over x cubed is the derivative of 3 over x squared, and multiply by e to the negative 3x. So then at this point, we want to set the second derivative equals to 0 to find point of inflections. And then I can see that I have e to the negative 3x is common terms. And I have e to the negative 3x. And I have 9 over x to the 4 minus 6 over x to the 3 equals to 0. And I have e to the negative 3x. I can pull 3 over x cubed out. And then what I have is 3 over x minus 2 equals to 0. So at this point, I know that x equals to 3 over 2 is the only point of inflection. Is that the only points of inflections? So inflection points of inflection are points where the second derivative equals to 0 is all, and also there are points where the second derivative is undefined. So if you look at the second derivative here, x equals to 0 is the point where the second derivative is undefined. So you have 2 points of inflections. X equals to 0 and x equals to 3 over 2. All right. And if we pay attention to the domain of the functions, x has to be different than 0. Okay. So now we can create a table. So I'm considering this function from negative infinity, right, to positive infinity. And the 2 points of inflections are 0 and 3 over 2. Okay. Then I would write down my interval test. 0, 3 over 2, 3 over 2, and positive infinity. And then from here, I pick a point in each interval. I say negative 1, 1, and then 2, right? And then I would use the second derivative to test this point. Okay. And you can use a calculator to see what are the sign of each of these values. Let's go to so we look at this table here, you can see that the second derivative, this is the functions that we're working on. And the second derivative of the functions at x equals to negative 1 is positive, right? I don't care the value, I just need to know the sign. So it's positive, and it's positive, and it's negative. If we look at the table here. So positive at negative 1, positive at 1, and negative at 2. So then what is the conclusion that we can make about the concavity of the graph? So that means the graph here on the interval from negative infinity to 0 is in concave up, because the second derivative of the test value is positive. It's concave up. Okay. And the graph on the interval from 0 to 3 over 2 is also concave up. And from 3 over 2 to positive infinity is concave down. Okay. So we look at the graph, it's clearly that from negative infinity to 0 is concave up. And from 0, right, to 3 over 2 is concave up still, and then after 3/2 is concave down. All right. So you can write a conclusions for these functions here. So f of x is concave up from -infinity to 3/2, and f of x is concave down from 3/2 to positive infinity. Okay, we go to the next example, and it's a polynomial, but again, in order to find the points of inflection, you need to find first the first derivative, which is 3x squared minus 6, and then you're gonna find the second derivative equals 6x. Okay, then you set the second derivative equals to 0 to find the point of inflection, which is x equals 0, and which is the only point of inflections that you can create a table, right? Go from -infinity to 0 to positive infinity, and you can pick first you want to create your test interval, and then you pick a point which is -1 and 1, and then you want to find the sign of the second derivative, and in this case it's simple enough where you can just, so 6 to -1 is -6, so negative and then positive here. Then your conclusion is the functions is concave down from -infinity to 0 and concave up from 0 to positive infinity. So conclusions. F of x is concave down on the interval from -infinity to 0. And f of x is concave up on the interval from positive infinity, 0 to positive infinity. All right. This is test value, this is sign, and this is conclusions, right? Okay. So let's see if it's right. So as you can see that the 0 here is a point of inflection, is concave down from -infinity to 0, and is concave up from 0 to positive infinity. Okay. And then the next example is you look at each functions, you find all the relative extrema. Second, you use a second derivative test where applicable, right? Then you want to graph a function of f of x. To find all the relative so you find all the relative extrema by using the second derivative test. Again, all the relative extrema occur at critical point, a point where the first derivative equals to 0. So the goal is we still need to find all the critical points by finding the first derivative. Okay, and then you set the first derivative equals to 0 to find all the critical points. Okay. All right. So now you need to use a second derivative test, right? Which means you find the second derivative of the functions, and then you plug these critical points into the second derivative functions. So then, but first I need to find the second derivative, right? From the first derivative, I can take the derivative again to find the second derivative, which is 6x minus 6. And then I plug 0 into the second derivative to get 6 times 0, negative 6, is negative 6. And then if I plug 2 into the second derivative, I got 12 minus 6, which is 6. So negative 6 is less than 0. Positive 6 is greater than 0. Using the second derivative test, if the second derivative at the critical point is less than 0, that means this point here is on the concave down interval. If it is in the concave down interval, that means this point here is a local maximum. And again, if the second derivative at a critical point is positive, that means is on the concave up interval. If it's on the concave up interval, that means this point here is a local min. So what is your conclusions? Your conclusion is f of x has a local maximum value when x equals to 0. And f of x has a local minimum value when x equals to 2. Let's go to the graph of these functions. So as you can see that when x equals to 0, f of x has a local maximum. And when x equals to 3x squared, not 2. When x equals to 0, f of x has a local maximum, and when x equals to 2, f of x has a local minimum, which matches to what we have here. All right, again, in order to find all the relative extrema, you need to find all the critical points. In order to use a second derivative test, you need to find the second derivative functions and you plug all the critical points into the second derivative functions to determine whether those critical points are a local maximum or local minimum. Well, let's do another example here. So your function's f of x, right? And then you need to find the first derivative, which is 16x minus 1 over x. Then you set this functions equals to 0. (16x) equals to 1 over x. I mean, 16x squared equals to 1, so then x equals to plus and minus 1 over 4. But again, in this case, this functions here is only defined. So the domain of these functions is just from 0. 0 is not included to positive infinity, okay? Because you have a natural log functions, natural log of x, and the domain of the natural log of x is from 0. 0 is not included to positive infinity. And when you found there's two critical points using the first derivative of x, but we only taking one critical point, which is the positive one, because the negative 1/4 is not even on the domain. Is any other critical point that we can have? So another possible critical point is x equals to 0, right? But again, 0 is not in the domain, so we don't have to worry about it. So x equals to 1/4 is the only critical point. And again, in order to use the second derivative test, we need to find the second derivative of the functions. So the second derivative of x equals to 16 plus 1/x squared. Okay. And if you look at the second derivative here, 16 is a positive number. X squared is always non-negative. So 16 plus 1/x squared is always positive. So that means the second derivative of the function is always positive on its domain. That would tell you that the function is always concave up on this domain. Okay, if it's always concave up and the critical point here, and you have one critical point, then you know for sure that this critical point here has to be a local minimum. That's what we know from our observations. But then if we still want to use a second derivative test, we would like to plug this critical point into the second derivative. So f double prime of 1/4 is 16 plus 1/4, 16, right? 1/16 should be 32, positive. Then using the second derivative test, f of x, the function f of x has a local minimum at x equals to 1/4. Again, this lecture introduces the concavity of the functions, how to determine on which interval a function is concave up or concave down. And you can use a second derivative test to locate all the local extrema. And again, local extrema only occur at critical points. Those are the points at which the first derivative of the function is equals to 0, or the first derivative of the function is undefined.